Hi everyone, I'm Professor Burgasser, and in this video we're going to be looking at how we calculate the forces resulting from drag or from viscous motion as an object moves through a fluid. Anytime an object moves through a fluid material, that's a material that can move and change density and flow, you end up with these drag forces that act in the opposite direction of motion. And a simple conceptual way to think about why this is, if we've got, say, a ball that's moving at some speed through a fluid, then that fluid is going to move in order to get around the ball. Obviously, it can't be in the same place as the ball, and so the fluid deflects around the ball as it goes through. Now, anytime we change the speed or velocity of any thing that has a mass, then you're going to have to apply an acceleration. So this deflection of motion, of course, requires an acceleration or force acting on the air to change its direction. And of course, this is the force that's applied by the ball itself, is the ball pushing on the air. And as we know from Newton's third law, you have to have an action-reaction pair, and so the force of the ball pushing on the air is countered by the force of the air pushing on the ball, and the net force resulting from that is a drag force that goes in the opposite direction of motion. So we can get that just from a simple application of Newton's three laws. Now, in reality, we can write down our expression for the drag force. It will depend on the speed at which an object is moving through the fluid. And so if we're going at a slow speed, this is commonly written as minus b times some constant, which we'll just call bs, times the velocity of our object relative to the fluid. And this is just the slow drag force, and it depends literally on velocity. And this constant depends on all sorts of different things about the fluid, the object, the size, all sorts of different factors that we'll get into in just a moment. Now this is the case for slow speed. We can also write a drag force at high speeds, which depends on the speed squared. And it just happens empirically that when an object moves fast through a fluid, that drag force actually increases much faster. It goes as a speed squared as opposed to the linear speed. And again, that just depends on some coefficient out front, which depends on the geometry, the fluids, etc. Now, this gives rise to an interesting phenomenon called free fall, because if we drop this same ball in the gravitational field here on Earth, we just let it go, all right, there is a force acting on the ball to accelerate it in the downward direction. But of course, as it accelerates downwards, it means that it's increasing its speed in the downward direction. And so we increasingly get a drag force that points in the opposite direction, against weight. And that drag force is going to get stronger and stronger as we get to higher speeds. And at some point, it's possible for the drag force to equal the weight. So if we have the case where the sum of our forces in the y direction, which is in this case equal to our drag force minus our weight, and that's equal to 0, then we have the case of terminal velocity. And that's going to be the case where the velocity is constant, it doesn't change. And in fact, we can even solve that very simply here in terms of our expressions for the force law. For slow speeds, this terminal velocity is going to occur when bs times the velocity is equal to mg. So that terminal velocity is equal to mg divided by this coefficient out front. And for fast speeds, our terminal velocity is going to equal to the square root of mg divided by the coefficient out front. Now keep in mind that these coefficients are going to be different because they depend on the units of the term in front of them. So in this case, it's going to be newtons per meter per second, or newton seconds per meter. This is going to be newtons per meters per second squared, or newtons squared, second squared divided by meter squared. So that's going to work out unit-wise in terms of this terminal velocity. But in either case, you can write down that pretty easily just from the expression for a drag force if you know what that coefficient is in the front. Now to go a little bit deeper into the motion of an object as it's being affected by drag force, let's look at a simple case of just one-dimensional object falling down in gravity and have just linear drag force acting on it. This is the case if you're dropping an object, say, in a very viscous, thick fluid, and where you don't get the velocity that goes up very high, that's generally where we see linear viscosity or linear drag force. So a simple question is, what is the velocity as a function of time? Can we draw a velocity versus time diagram for an object that's falling in a viscous fluid? Well, I've drawn already the force diagram to approach this problem, all right, which we drew in the last slide. We have gravity pulling this object down, and as the object speeds up, it gets faster, drag force starts to kick in, and of course it's going to increase as the speed gets stronger. So we have the drag force acting in the opposite direction, and the magnitude of that drag force is B times V. Now notice I didn't write minus BV. The minus in the last expression was indicate the direction of the motion. The magnitude of the force is just this coefficient B times the speed of the object. It's important to make sure you write that as a positive number because that's indicating a magnitude. Well, we can just go ahead now and write down Newton's equations for this force diagram. Right? The sum of the forces in the y direction are just going to equal to mg, because I'm writing my y coordinate to go downward, minus b times v. So we recover our minus sign just because of the direction of the arrow. And that's equal to the mass of the object times its acceleration. And I'm just going to rewrite this by dividing through by mass, so I'll get an acceleration is equal to g minus b over m times the speed. Now notice if we have the case where the drag force is negligible, and that's the case where this b coefficient goes to zero drag force, you get back exactly the same expression we had before. The acceleration is just equal to the surface gravity acceleration. But now we have this extra term that's going to reduce the amount of acceleration by this b over m times the speed. And this is a deceptively simple looking equation. Of course, the problem is that the speed is changing with time, which means the acceleration is changing with time, and the acceleration is the thing that's telling you how the speed changes with time. So there's kind of this recursive loop. So we're going to have to approach this from a calculus perspective to see if we can actually solve how the velocity changes as a function of time. Now it turns out it's not that hard because remember our acceleration is just equal to the change in the speed with respect to time when we're looking at it from this one-dimensional perspective. So this now is a linear differential equation that we can use our regular mathematical tools to solve. So to solve this problem, we're going to do a little change of variables in order to get rid of this one constant out here, the surface gravity, and turn this into a much simpler one-dimensional linear differential equation. And the substitute I'm going to make is to change my velocity term into its original velocity, but I'm going to subtract off this combination of mg over b. And if you remember from the last slide, in fact, what I'm subtracting off is the terminal velocity for this linear viscosity term. And notice that the derivative of this new velocity is exactly the same as the derivative of the last one because I'm just subtracting off a constant term. But the reason we're sticking this in here is that when you add in, so if I move this to the other side, we got v prime plus mg over b equals velocity. When I stick that into this term, that's going to conveniently cancel out my gravity term on that side. And we're going to end up with an expression that's dv prime dt prime is just equal to b over m times v prime. And this is a much easier expression to work with because I can also rewrite this as dv prime over v prime is equal to, and I have to be careful, this is equal to minus b over m. So that's minus b over m times dt. And this is now ripe for an integral because all I have to do is add my integral signs around these two things, and notice that I'm going to be integrating from some initial velocity, and that's an initial v prime, to final velocity, and our initial time, oops, and don't need a prime there, to our final time. And this is now the integrals that we need to solve in order to solve for the motion at any time along this path. So to solve for these integrals, we just have to go back into our tables of integrals and figure out how we actually solve for something like dv over v. It turns out that the integral of that is just equal to the natural logarithm of v prime. So we can write down the solution as log of v prime, evaluated from our initial v prime to our final v prime. And remember, keep in mind that v prime is this change in variables we've done over here. And that's equal to minus b over m times the integral of just dt, which is just the difference between our final time and our initial time. Now, the logarithm here, so let's write out these terms. This is log vf prime minus log vi prime. And one thing to remember about logs is if you're subtracting off two logs, it's equal to the log of the ratio of the terms inside there. So this is just equal to log vf prime over vi prime. And again, that's equal to minus b over m times the differences in times. Now, I've got an expression here in terms of logs. Logs are not usually something we like to deal with all the time in sort of writing down physics problems. But let's actually isolate this term by taking both sides to the exponential power. All right, and the opposite function of log is e to that power. That's the exponential. So this means that we can write down vf prime over vi prime is just equal to e to the minus b over 2m times our difference in times. All right, now it's a little useful at this point to sort of go back and rewrite our terms in terms of what we originally had. Remember that we changed our variables to this v prime, which is velocity minus mg over b. And so we can substitute that back in, and noting that the initial velocity, which is stated here, it's dropped from rest. So that means that our initial velocity is equal to 0 meters per second. So our initial velocity prime, which is this v, is equal to minus our terminal velocity. All right. So, so that means that we can write down our vf prime as just our final speed minus our terminal velocity. And this is going to equal, if I multiply both sides by our initial vi prime, which is just minus vt, this is minus vt exponential b over 2m. And I'm just going to write down t because I'm going to assume that the initial time is equal to 0 seconds. I'm free to choose that as I will. All right, so we can now group our terms. So we're going to have a final velocity. If I add vt on both sides, this is going to equal to our terminal velocity times 1 minus e to the minus b over 2m times time. And this is our final expression, noting, of course, that our terminal velocity is just our mg over b. Now, this is a very common expression for any kind of process that has a decay aspect to it, whether it's decaying radioactive decay, or in this case, the slowing down over time, or the slowing down of the speeding up, I should say, the slowing down of the acceleration over time. You often have this sort of declining exponential term with an asymptotic value, which is the terminal velocity. So let's look at it a few times. If we look at it, for example, at t equals 0, what we get is this term is e to the minus 0, which is 1. We get 1 minus 1. That means our final velocity is equal to 0, which is what we started with. That's our initial velocity. All right, if we look at a very long time, so let's say time goes all the way to infinity, then this is minus b over 2m times a really large number. E to the minus that is basically 0. And that means that our final velocity turns into the terminal velocity. And that's exactly what we predict for our motion. As this drag force increases, eventually it matches the weight force, and then the velocity stays constant, and that drag force stays constant as well. And of course, the weight force is always constant. So if we were to draw this, then we're going to start at a 0 velocity at time 0. We're going to end up at some terminal velocity at some late times. And what you'll find is that this expression looks a little bit like this. This is an asymptotically rising velocity, and it asymptotes at the terminal velocity, right? Increases, and then it decreases with time. That just tells us that the slope is decreasing. The slope of the velocity versus time curve is just the acceleration. That's just telling us that the drag force is approaching the weight force, so the net force is going down, and the acceleration is going down, and that's exactly the kind of curve you would expect for this kind of motion. Now let's look at an example of the faster drag term, the drag force that depends on speed squared, because this is commonly the drag force that's seen when objects are moving through the air. The air viscosity is so low that objects can get to very high speeds before they're significantly slowed down by the drag force. And so this is something that's common when we're looking at things thrown in the air, parachuters jumping out of planes, etc. So as I said before, the drag force is going to depend on some constant out in front times the speed squared, and it's going to act in the opposite direction of the motion. And it's often a common expression for this coefficient out in front is the following, where it's equal to 1/2 times the density of the fluid in which the object is moving times the area that's projected along the motion. So that's the sort of area that the fluid sees. And then there's another term called the drag coefficient, and this is just something that takes into account the shape of the object. Obviously something that is a flat surface that's moving through the air is going to have a very different drag force acting on it than something that is aerodynamically shaped, very pointy shaped, very fluid lines, is going to move with a lower drag than something that is just pushing right through like a brick wall. So all of these terms come about just from experimental analysis. You can also check that the units make sense. Density is something that is kilograms per meters cubed. Surface area is meters squared. And the drag coefficient is just a dimensionless quantity, so that doesn't factor in. When we combine these numbers together, that gives us kilograms per meter. But if I then multiply it by our speed, which is meters per second squared, this gives us kilograms meters per second squared, which is our force term. So dimensionally, this property for the coefficient of fast drag matches our units that we need in order to have a force come out of it. Now we can write down then the terminal velocity at these fast speeds, because we already know that it's going to equal to the force of drag is equal to the weight. And so our expression is the weight divided by our fast coefficient and then square root, because it depends on the speed squared. If I then stick in my terms, you can see this is going to be equal to 2mg divided by rho f times the area times our drag coefficient. And notice that the drag coefficient enters here at the bottom, and so as the drag coefficient goes up, our terminal velocity will go down. And so objects that have very flat surfaces tend to have drag coefficients that are closer to 1. Whereas if you have something that has a very sharp feature of aerodynamic shape to it, you're going to have a smaller coefficient of drag, which means you have a higher terminal velocity. And parachutists manipulate this drag coefficient all the time as they move their bodies through the air in order to change their relative speed as they reach terminal velocity. So let's look at a specific quantitative example of this in the area of baseball. We can look at what is the drag force acting on a thrown baseball at 100 miles per hour. So this is a baseball pitched by some of the fastest pitchers in the National League, and we can see what kind of drag force is acting on that baseball as it's going from the pitcher's mound to the batter. So we need to sort of figure out some of the constants to put in here. One thing we can look up, for example, is the size of the baseball. So R turns out to be, for regulation baseballs, about 35 millimeters. And we can translate that into our meters, 0.035 meters, because millimeters is 1/1000th of a meter. We have a regulation mass for baseballs, which is about something like 150 grams. And again, converting this into our SI units, that's 0.15 kilograms. In order to calculate this terminal velocity terms, we've got mass, we've got to figure out the density, and this is just the density of air. And again, you can look that up. It's about 1.28 kilograms per meter cubed. So every cubic meter of space around us has about a kilogram of air. The coefficient of drag, CD, for a spherical object is something like 1/2. Now it's going to vary a little bit from baseball to baseball because baseballs have these little ridges around them, so that actually increases their drag coefficient slightly. But let's take just an average value of about 1/2. And we have our initial speed, which we are given in the problem, as 100 miles per hour. But again, let's convert that into our SI units. That turns out to be about 45 meters per second for our speed. Now to be complete, let's make sure we draw a force diagram on this ball as it's moving from the pitcher to the baseball, the hitter. So if I have our baseball and it's moving in this general direction. That baseball has, of course, a mass, and so it's got a weight, and that's going to pull that baseball downwards by mg. And then we have a drag force that's acting on it, and of course that drag force is going to act in the opposite direction of motion. So at least initially that drag force is going to be pulling that baseball backwards. Of course, as the baseball starts to fall down, that drag force is going to tilt slightly. Let's consider the case, just for now, of the drag force being purely horizontal. All right, now, at what point do we reach a terminal velocity? Well, let's actually calculate the terminal velocity for this case. And that's just a matter of putting in our expression here for our coefficient of our drag coefficient, our fast drag coefficient. All right, BF is just equal to 1/2 times the density of the fluid, which is 1.28 kilograms per meter cubed. And then we're going to multiply by our area, but our area is just pi times r squared, right? The area is the circle at which the baseball shows the fluid as it moves through. So if the baseball has a radius r, that circle is just pi times 0.035 meters squared. And then we have our coefficient of drag, which is 0.5. So if we write all these numbers out, we'll get a number of 1.3 times 10 to the minus 3 kilograms per meter. Now that's an unusual unit, but that's just the units it has to have once you multiply by meter squared per second squared to give a unit of force. All right, so that gives a kind of general idea of the size of this BF term when you're looking at objects that are moving through the air. And it's relatively small when you think about it. All right, so now we can actually compute the drag force, because it's just our 1.3 times 10 to the minus 3 kilograms per meter times our speed, which we calculated to be 45 meters per second squared. And we write out this number, what we find is a force of 2.5 newtons, which is a fairly small number. Now notice again, I've been careful here about making sure I use the correct number of numbers of significant digits. I was a little bit sloppy here because I used 0.5 as one significant digit. In fact, we can make that 0.50 because that's about the level that we know that drag coefficient. But throughout here we're keeping our significant digits. I just want to make sure we point that out. Okay, so that's the force acting on the baseball. Let's look at the acceleration of the baseball due to this force. Well, that's just equal to the force over its mass. All right, so we've got 2.5 newtons divided by the mass, which we worked out to be 0.15 kilograms. And that's going to equal to this is equal to 17 meters per second squared. And if you think about that, that's equal to 2 times our gravitational acceleration. So the drag force, as this thing is being released, has an acceleration that's twice that of the acceleration that's pulling it downwards. The drag force is clearly important in the motion of the baseball because it's actually a much larger acceleration and a much larger force than the weight force that's pulling the baseball down. All right, so now let's compute the terminal velocity. All right, we've got our expression here. In fact, we can just use our mg, which is 0.15 kilograms times 9.8 meters per second squared, divided by our coefficient of fast friction, which is, we've already calculated as 1.3 times 10 to the minus 3 kilograms per meter, square root. Here's a good time to sort of make sure that we've got our units right by canceling our kilograms. And we can cancel, we can't cancel actually, it's 1 over meter, so that's going to give us a meter on top. So we're going to have meter squared per second squared. The square root of that is meters per second, so we've got the right units. And then if we write out the actual numbers, this works out to be 34 meters per second. Now, what's important about that number is that it is greater than our initial speed of 45 meters per second. So that means that if we were just looking at this from a terminal velocity perspective, that's if we were just dropping the ball at this speed is higher than the terminal velocity. So the drag force is actually going to be greater than the acceleration due to, or the weight force that's acting on the ball as it's falling down. So in any case, this is going to tell us that even if we threw this ball straight down at 45 meters per second, it would still slow down because the terminal velocity is less than the speed that we're throwing at. Now, of course, in this case, we've got a ball that's being thrown horizontal, so we don't have that weight term acting in that direction. So it's definitely slowing down, and it's slowing down quite quickly because of this acceleration term. But in either case, this is a ball that's being thrown faster than terminal velocity, so no matter what happens, which way we throw it, it's going to go slower as a result of the interaction with the air.